NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn how to solve a homogeneous system of two quadratic equations in two variables using a very visual trick, the substitution y equals mx, where m is y over x. Here is the general form. Each term involving x, and y is total degree 2, so we call it homogeneous of degree 2. Our key idea: let m be the ratio y over x, so y equals mx. We assume x is not 0. We will handle x equals 0 briefly at the end. Substitute y equals mx into both equations. Every term now has a factor x squared. Factor x squared out of each equation. Because x squared is not 0, divide the equations to eliminate it. Cross-multiply to get a single equation in m. It is a quadratic in m with these coefficients. Solve this quadratic for m. Then find x from either factored equation, and recover y equals mx. Let's solidify with an example. Solve the system. X squared plus y squared plus 2x, y equals 25, and x squared plus 4, y squared minus 2x, y equals 13. Build the quadratic in m using the coefficient recipe. The discriminant is 1600, giving m equals 2/3, or m equals 6 over 29. Use the first factored equation to find x squared equals 25 over 1 plus m squared plus 2m, which is 25 over 5/3 squared. So x equals plus or minus 3, and y equals plus or minus 2 with the same sign. For m equals 6 over 29, we get x equals plus or minus 29 over 7, and y equals plus or minus 6 over 7 with the same sign. Those give 4 solutions in two opposite pairs. Edge case: if x equals 0, substitute x equals 0 into the original system and solve directly for y. If consistent, include those solutions too. Summary: recognize the homogeneous degree. Substitute y equals mx. Factor out x squared, divide to remove x squared. Solve the quadratic for m, then back substitute to get x and y. Example: we will solve the quadratic system x squared plus y squared minus xy equals 3, and y squared minus x squared equals 3. We will use the homogeneous substitution y equals mx to reduce the system. Because each term is degree 2, setting y equals mx traces rays through the origin. Substitute y equals mx into both equations. Now divide the first by the second to eliminate x squared. Substitute m equals 2 back into system I. Let us visualize the solutions on the coordinate plane. The substitution y . In this lesson, we will prove that a certain nonlinear system has real solutions. We will turn the system into a single quadratic equation in x, and then show its discriminant is positive, which guarantees real roots. Here is the problem. We are given the system ax squared plus by squared equals x minus y, and ax plus by equals m. There is also a condition. The absolute value of square root of ab divided by a plus b is less than 1 over 2m. We will use this inequality to prove the system has real solutions. First, read off some immediate consequences of the inequality. We must have ab greater than or equal to 0. So the square root is real, a plus b is not 0. So the denominator is defined, and m is positive, so that 1 over 2m makes sense as a positive bound. We will consider two cases, b equals 0 and b not equal to 0. This simple split will let us either solve directly or reduce to a single quadratic in x. Case 1. If b equals 0 and a is not 0, then the system becomes ax squared equals x minus y, and ax equals m. These are clearly real relationships, and we can read off real values of x and y, so the system has real solutions in this case. Now, the main work is case 2. When b is not 0, we solve the linear equation for y equals m minus ax all over b. Next, we will substitute this into the first equation. Substitute y into the first equation. We get ax squared plus b times m minus ax over b quantity squared equals x minus m minus ax over b. Multiplying through by b and expanding will give a quadratic in x. Now expand and gather like terms. After simplification, The left side minus the right side equals 0 becomes a times a plus b times x squared, minus a plus b plus 2ma times x plus m squared plus m equals 0. Compute the discriminant. Delta equals negative of a plus b plus 2ma squared, minus 4 times a plus b times m squared plus m. This simplifies beautifully. We obtain delta equals a plus b squared minus 4abm squared. Finally, use the given inequality. From the absolute value inequality, 2m times square root of a b is less than the absolute value of a plus b. Squaring both sides gives 4m squared, ab less than a plus b squared. Rearranging shows delta is positive. Therefore, our quadratic in x has two distinct real roots, and consequently the original system has real solutions. Recap. We split into two cases. If b equals 0, we read off real solutions directly. If b is not 0, we reduce the system to a quadratic in x with discriminant delta equal to a plus b squared minus 4abm squared. The given bound makes delta positive, hence real solutions exist. That completes the proof. In this lesson, we will eliminate the variables x and y from a symmetric quadratic system and derive clean relations among the parameters p, q, s, and t. We'll proceed in two cases, first when t equals 0, and then when t is not 0. Here is the system. We are given equation 1x plus y equals p plus qxy, and equation 2x equals s plus tx squared, and 2y equals s plus ty squared. Our goal is to eliminate x and y and obtain relations that only involve the parameters p, q, s, and t. Case 1, t equals 0. Then equation 2 becomes 2x equals s and 2y equals s. So x equals s over 2 and y equals s over 2. Substitute these into equation 1 to get s equals p plus q times s squared over 4. Rearranging gives the compact parameter relation qs squared minus 4 times the quantity s minus p equals 0. Case 2, t is not 0. Because the system is symmetric in x and y, we look for solutions where x equals y. Setting x equal y in equation 1 gives 2x equals p plus qx squared, or qx squared minus 2x plus p equals 0. From equation 2, we also get tx squared minus 2x plus s equals 0. Subtract the two equations to eliminate the linear term, q minus t times x squared plus p minus s equals 0. Hence, if q is not equal to t, x squared equals s minus p over q minus t. If q equals t, this forces p equals s. Next, use 2x equals s plus tx squared to express x in terms of the parameters. Substituting the x squared expression yields 2x equals s plus t times s minus p over q minus t, which simplifies to 2x equals sq minus tp over q minus t. Square this x and match it with x squared equals s minus p over q minus t. This produces the clean parameter relation, parent t p minus qs parent squared equals 4 times parent q minus t parent times parent s minus p parent. Summary. If t equals 0, then qs squared minus 4 times s minus p equals 0. If t is not 0, the parameter relation for symmetric solutions x equals y is parent tp minus qs parent squared equals 4 times parent q minus t parent times parent s minus p parent. These identities eliminate x and y and tie the parameters together. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.